Hey everyone, we're going to start our 11-6 class notes. We're going to spend 3 days on 11-6. We'll review and then we will take the chapter 11 test. So today with solving some more log equations, we're going to see more complex log equations. We've already seen log equations where we just switch forms and then we would solve. So a little bit more complex today. We're going to use some condensing to get us to our final answer for our solving. I just want to remind you that, and we're going to learn about natural logs, but I want to remind you that the common log is log of x. The common log has a base where you don't see it, but you need to know it. You need to know that it is base 10. The natural log is ln. L for log, n for natural, but backwards, ln of x. That's how you say that. So log and natural log. This is still a log. It's just considered a natural log. And the natural log of x has a base e. So that's something I'm saying. I'm not writing it down, but I definitely think that you should write it down. It has a base of e. And maybe in chem you guys have talked about e. E is a number. It's like pi. It continues on. But e's number is approximately 2.71. And so, again, just two different types of logs. And again, in math and science, they are used. Moving on to our next slide. So I don't really like that I numbered these. I kind of feel like these are similar to verifying, like our hints. You just try some of these methods to solve. So each problem is going to look different. And so one of the methods we can try is transform the equation so that there's a single log appears on one side, which means what I'm saying there is that you want to condense. On the left side, you always only want to see a single log. You only want to see one log. On the right side of your equation, you only want to see one log. If there's log on both sides, there might not be. If you have a log on both sides, then you can use the method that number 2 is saying, which is there's property that says if you have the log to the same base on the left and on the right, you can take the value piece of the log and set them equal and solve. If when you transform and there's only a single log on the left or just a single log on the right but not on both, then I would do what number 3 is saying. Then the method that I would use for solving would be to write it in exponential form, which means switch forms. And then obviously our ultimate goal is to solve. So we're going to go ahead and start these examples. Here's our first one. And when I look at this, I see just a single log on the left. There's no addition or subtraction with logs. And on the right, I don't see a log at all. So this is pretty similar to what we've solved already in 11.2 or 11.3, whatever that was. I think 11.3. So this tells me one log in my problem. I have a base, I have an exponent, I have a value. I'm just going to switch to exponential form. Base of 3, exponent of 3 equals the quantity of x plus 1 to the 5th power, which is the value. And now they don't have the same exponent, so I can't set the bases equal. I need to, and really that's all about the base being equal and setting the exponents equal. A lot of students were doing that in homework, same base or same exponent, they were setting the bases equal, but that's not what the property says. So I'm just going to find out what 3 cubed is. On our power sheet, we can see that that's 27. 3 cubed, 27. And then I have the quantity of x plus 1 to the 5th. Now, I would not want to write this out 5 times and multiply that. I would rather just get rid of the exponent, which means I can take this to the 1/5 power, or I can take the 5th root of it. So I'm going to go ahead and take the 5th root of 27 and the 5th root of this quantity to make those cancel, leaving me with x plus 1 equals the 5th root of 27. So I'm going to go to my perfect fifths, and 27's not here. So I'm going to get decimal answers here, and that's okay. In 11.3, when we solved logs, we just had exact values. And so seeing that some values might have decimal answers, some log equations could have decimal answers. So I'm going to subtract over the 1. remembering that the fifth root of 27 is just a number. It's just a decimal that keeps going. So yes, these are technically like, and so yes, I can subtract a number from a number. So I'm going to take my calculator and show you how to put in the fifth root. I believe it's in math. And if you pick option 5, you will get, and you want to go back and change that to a 5. You don't want the A and S piece there. So let's make sure we delete that if that showed up on yours. Delete. We have the fifth root of 27. And then on the outside, so make sure you arrow away, -1. And so we get 0.933. I'm just going to round to the hundredths because that's normally what I do. So 0.93 is my solution. Just take a quick second to make sure that that's not going to make your value of a number that you shouldn't have here. So positive number plus 1, that's still going to stay positive to the fifth. We're good there. All right, moving on to the second example. Here's where I recognize on the left side, I have log base 8 plus log base 8. So I have 2 logs on the left, which we don't want. So here's where condensing comes into play. We know that we can condense these. We can write these as 1 log. When we see addition, we know the property says that we need to multiply the values. So I'm going to write this as log base 8 of 3 times the quantity of 2x plus 5 equals log base 8 of 33. Now on the right side, I see a log as well with the same base, which is important as well. These are both log base 8. And so now we can use what number 2 says. We can use that property and just set our values equal. At the same time that I'm going to set these equal, I'm going to distribute here. So I'm going to say 6x plus 15 equals 33. I'm going to subtract over the 15, get 6x equals, borrow, it's going to be 18. Yeah, 18 is what we're going to get there. And then we're going to divide by 6. And here we get an exact value, but we could also get a decimal here as well. So x equals 3. And then just again, 6 plus 5, that 11, we can have an 11 there. That's the only place where x is, so our x is 3. And then we are finished with that example. Our third and final example for today. I see and recognize that I have 2 logs again on the left and no log on the right. I still want to condense. Anytime you have several logs, you want to condense. What stands out to me is the logs are being subtracted, which tells me I need to divide the values. I need to divide those values. I'm going to write this as 1 log, log base 3 of 2x over 3x plus 15 equals -2. And now I'm going to switch forms because I don't know how to solve log equations besides switching to exponential and trying to get my x alone. So I know that this is the base, I know that this is the value, and this is the exponent. So when I switch to exponential, we write exponentials with a base and a power equal to a value. And then I'd probably just take care of this negative exponent piece and write that as 1/9, right? 1 over 3 squared. And I'd probably just solve this as a proportion, cross multiplication. So I'm going to move up here just so that I have more room. Cross multiplying, I get 18x equals 3x plus 15. And then I'm going to subtract over the 3x. And I get 15x equals 15. And then I divide by 15. And x equals 1. Then I just double check. 2 times 1, yes, we can have a 2 there. 3 times 1 is 3 plus 15, 18. Yes, we can have an 18 there. Our solution is x equals 1. Okay, that's some more solving log equations. Hopefully that's clear. If not, please ask questions. Bye, everyone.